Today's video will demonstrate how to use polymorphism. Hello, I'm James Helfrich. Polymorphism is one of the most powerful tools we use in object-oriented programming. However, without understanding how it works, it can be easy to fall for a few pitfalls. Now, we're going to do a demonstration in C++ because C++ gives us direct access to pointers, and through pointers, we could do late binding, and late binding is how polymorphism works. First, let's talk about early binding. Early binding, also known as static binding and compile time binding, is a flavor of binding that a compiler performs before the program is executed. And so there's three flavors. The first of them is with variable binding tables. Every time you declare or use a variable, then the compiler creates a binding table, which has the name of the variable, the data type, and its location in memory. The compiler does the same thing with functions. Every time a function is declared, then the compiler creates a function binding table entry, including the name of the function, the return type, the parameters, and anything else is required, as well as a location in memory where that particular function is compiled. The final type of binding is called data type binding. Now, the compiler is going to pre-build a binding table for the built-in data types, int, floats, bools, chars, and stuff like that. But it will also create a binding table for all the data types that you create, whether these be classes or structures or enums or type defs or whatever. Every time a new data type is created, then an entry in the data type binding table is added. To demonstrate this, I'll start with two variables. And these can be early binding variables, just regular stack variables. I'm going to call them, let's see here, pi, 3.14159, and e as well. And now when I create these two variables, then 3.14159 and 2.71 have to exist somewhere in memory. So the compiler is going to create a function, a variable binding table, one with the value pi and the address where that's located in memory, and the next with the value e, where it's located in memory. And then, of course, when I say cout pi and cout e, then the compiler will say, hey, look, pi actually corresponds to some random location in memory, df734968 or something like that, and then it will retrieve the value that's in memory, and that'll be this value. And sure enough, I have my two values correctly retrieved from memory. Now, the same thing happens when I create functions. In this case, I'm going to create two functions. And when I create a function, that name is going to be associated with the location in memory where this function happens to be compiled. And so here I have function 1 and function 2, so I'm going to have two entries. Now, when I'm finished, I'm going to call these functions using the traditional method. I'm going to say, hey, call function 1 and function 2. And when the compiler encounters function 1, it's going to jump to where function 1 was compiled and execute that code, and then when it encounters 2, it's going to jump to where 2 is compiled, and it'll execute that code, and that works as we expect. The second type of binding is called late binding, otherwise known as dynamic or runtime binding. Here, the program makes use of information the compiler does not have access to, usually runtime variables. And there are three flavors of this as well. First of all is pointers. Anytime the program uses a pointer, then the compiler cannot tell where that pointer is going to be. And this mostly is used with arrays because the compiler cannot tell the size of the array nor its location, especially if it's dynamically allocated. This decision is made at runtime. The second is function pointers, otherwise known as callbacks. And here, the compiler cannot tell which version of the function is being executed. It could just tell that one of the versions is being executed. That decision is made at runtime. And the final is polymorphism. And once again, the compiler cannot tell which flavor of the function is being used, in this case, derived class. It could just tell that one of the flavors is being used. The decision of which flavor is being used is determined at runtime. How this works, we're going to create two variables, our double pi and our double e, just like before. And then we're also going to create another variable, which is a pointer to a double. And we'll call this p for pointer. Now, right now, p is going to point to null pointers, not going to point to anything. So I'm going to try to decide which variable p is going to point to, either pi or e. And I'm going to use an if statement for that. And right now, it's while if If true, P is going to point to pi, else P is going to point to E. Now the compiler can't tell which one P is pointing to, pi or E, so therefore this is a late binding. It's a decision made at runtime. So when I run this code right now, it's going to point to pi, sure enough, and then if I change this to false, it'll point to E. So this is a late binding decision. The compiler can never know who P is pointing to. In other words, I've kind of made my own binding table here with just one entry. And P is going to update its value that it's pointing to depending on some runtime logic. Now, it turns out I could do the same thing with functions. So I'm going to have a variable called PFN for pointer to function, and the syntax is awful. The return type void, the pointer name PFN, and then there's a 0 parameters. And right now it's going to point to, PFN is going to point to 1, or it's going to point to 2. Now since both the function 1 and 2 have the same function signature, then I can use the same pointer to refer to either one. Now when I execute this function pointer, the compiler has no idea which one is pointing to, either 1 or 2. That decision is made at runtime, so this is a late binding decision. It's utilizing information that is simply not available to the compiler when the code is compiled. Polymorphism is a process of one class having more than one variation, each of which honors the same contract, in other words, has the same public methods, but has different behavior. In other words, the derived classes have different implementations. So in this example, we have an account class, and the account class has 3 virtual functions: and get balance, insert transaction, and generate report. Now, there are 3 flavors of accounts: checking, savings, and credit card, each of which honors the same contract as account, but has different implementations. Now, to exhibit polymorphic behavior, we must have 3 things. The first of all, we must have inheritance. And inheritance will determine what the shared contract is, and that shared contract is defined in the base class. Without inheritance, we cannot have polymorphism. The second is we must have virtual functions. In C++, we use the virtual keyword to indicate there's virtual functions. And what this is going to do is it's going to create a vtable for that particular function. And the final is you must have a pointer. And this allows the program to decide which flavor is being utilized at a given moment in time, rather than a compiler. And that is the very essence of late binding. To demonstrate how this works, we're going to start with a class called base, which is our base class, and it's going to have a constructor which sets a value to 1,000. It's going to have a copy constructor, an assignment operator, and a display, and this display will say, hey, this is base's display. I'm also going to have a derived class which base is on, and it's going to have set the value to 99, and a copy constructor, an assignment operator, and this display will say, hey, this is derived display. Now I'm going to declare 2 objects, one of type base, and I'll call it base because I'm super original here, and one called derived because once again I'm not very original with my variable names here. Now if I call base.display and derived.display, I'm going to expect that base is going to say, hey, this is base : display, and here's my value, which is 1,000. And this is derived.display, and here's its value, which I expect to be 99. And let's see what happens when I run this code. So when I run the code, then sure enough, base gets called and derived gets called, just like we expect. Now, what I like to do is I want to assign derives value to base. Okay, so when I assign derives value to base, this is going to call the first of all, base's constructor is going to call this, going to call the assignment operator, which will assign value. Now remember, derived has the value 99 and base has the value 1,000, and we'll see here that once again each of the prospective methods is going to get called, but the value will get updated. Okay, now if I actually create int value here in derived class, now I'm going to have 2 versions of value, base's value and derived values. Those are going to be 2 separate variables. So when I run this, then, oh, look, the update didn't happen because I'm not actually changing the member variable. So I got to make sure I don't duplicate my member variables in my derived class if I want the inheritance to work. So I got to get rid of that guy. Okay, it's gone. All right, now, so the assignment operator does not work quite the way that I expect. because I'm kind of hoping that I'm going to get, when I assign derive to base, I'm hoping I'm going to get derives a display function to get called, and not bases. But here we have early binding at work because the compiler says, yo, I know what base classes display function look like, so I know what derives display function look like. This is all part of my binding table, so I'm not confused. Everything is good to go. Now remember, one of our prerequisites is I must have a pointer. So I'm going to make a pointer called p, and p is going to point to base. And this is one of my prerequisites for polymorphism. And so now, when I call p arrow display, then I'm going to expect to get bases display. Notice derived does not use in any capacity here, so let's make sure this works. And when I run it, sure enough, bases display gets called and the value 1000 gets called, so I'm not surprised there. All right, but now what happens when I call derived here? Now this is going to be kind of weird, because when I call this, then the data type of p is still a pointer to base, so I'm going to get bases display to get called. But I'm getting derives value. You see that? In other words, because display is still a regular function, it's not a virtual function, and the compiler knows what p is, it's a pointer to base, it's going to say, hey, I'm going to look at my early binding table, I'm going to call bases display, and everything's going to work. But now everything changes when I add the virtual keyword here. When I add the virtual keyword, now we're going to use polymorphism. Now we're going to use a v-table. And now we're going to use derives version of display. Isn't that cool? Okay, let's find out how this works here. I'm going to set a breakpoint here. And then when I jump into here, I'm going to bring up my my variable list, my watch window, and I'm going to look that base now has a v-table. Do you see that? In other words, there is now an entry in the v-table for late binding, its own function pointer table, and derived also has one. And when I look at p, we're going to see what version of p is. And when I expand p, it's going to say, hey, this is actually of type derived. And sure enough, there it is. It's of type derived. And that's how it knows which function to call, because this object carries around the function pointer referring to all the virtual functions that will be needed. And so it's going to know I'm going to call the right version. Now, when I kill that virtual keyword, and then I run the code again, let's bring up to my watch window, and notice there's no v-table. And so now we can't do late binding, we have to do early binding. Now we can't use the version of display that we expect, we have to use the bases version because p is a pointer to base. And that is absolutely the key difference here. With polymorphism, we need to have, number one, the v-table, which is going to be any method that has the virtual keyword. And we also need to have a pointer. And so whenever we have a pointer, then we're going to use the v-table's entry for display rather than the early binding table's entry for display. And sure enough, that guy is right there. Now, to emphasize how this works, I'm going to actually step into this function, and we'll see that even though it's a p base, I'm in derives version of display, because when I jump into that, it's going to access that function pointer, which is part of the v-table, just like we did at the very beginning. And that, sure enough, is derives this version of display. You can learn more about this in the polymorphism chapter of the software design textbook.